And I was hoping maybe I could get a volunteer to come up here to help me introduce why we might care. You want to just come up? All you got, I need 2 volunteers, so you guys can both be it. So one of you first, and then wait, first one of you. So just stand right there. All you got to do is have hand-eye coordination. Okay. So these, yeah, just come up here, right here. Yeah. All right, and so just stand right there. I'm going to throw these to you. These are foam, so it's not a big deal. So when you catch them, you're probably going to want to, you know what I mean? So I just want to point out here, notice there's some dots on these. And the dot is supposed to represent the approximate center of mass here, if I could do this. Pretty close to the center of mass, right? So it's where it's balanced. Now the whole point of this is when I throw this to him, I want you to watch this, and these points should hopefully become blurry, but the center of mass will be the point about which this rotates. And then what we're going to do is we're going to switch so he can watch and he can catch. Got it? So make sure you watch the dot. This is your only shot. Ready? Oh, shoot. Throw it back to you. Give it a good flip. Give it yeah, there we go. Ready? Watch that center dot. All right, let's try this. All right, whoops. Okay, and then switch so he can see. Go ahead, you can throw back or whatever. So try and just watch the dot. Maybe jump in the back of the class so you can watch the dot. Whip it. Go for it. Do you see that going about the center of the mass? All right, let's call that good. Let's give him a round of applause here. Thank you. All right. So I know that seems a little bit of a strange way to start the class. But one of the things that I wanted to talk about is why you should care about center of mass as a topic. So center of mass, sometimes you might see center of gravity. I'm going to call it center of mass, center of gravity, they relate. I don't want to go into the idiosyncrasies of that. You can take an engineering class if you want to learn more. Why care? Well, for one case, when an object rotates in, I'm going to call it free space, we can explain what that means later, but just imagine something's flying through outer space. It's going to rotate about its center of mass. I think that's useful enough just for that reason only. Imagine you launch something into space and it starts spinning. It's going to spin about that center mass. And you're going to see me write COM for center of mass, okay? That's number one. The other obvious reason is the force of gravity can be modeled as acting at COM. These are the two big things. So if you had, for example, we're going to learn about this soon. You don't have to know what these symbols are or what I'm drawing, but I'll try and explain this. Imagine you had a beam. And that beam is connected by some sort of hinge or pivot. We're going to learn about this more in chapter 12. And maybe there's a string. Okay? If we're going to learn that there are going to be forces acting on this, and up until now, all of our free body diagrams have just been a dot. But eventually, we need to draw the forces exactly where they are applied. And so the center of mass of the rod would be where the force mg is applied. Now, I don't know if you can tell where we're headed with this, but something that's on a pivot that can be free to swivel, that talks about rotation, right? Secretly hidden somewhere in there, there's something about rotation, and we'll learn about torque. So if we want to understand torque, we need to understand the center of mass as well. All right, Dom, anything else? These are the two things that jump out of my mind. Is there some other reason you think they should care about center of mass?
Yeah, those are two things to focus on.
These are the two big ones that we care about in our class. All right. And I mean, they're huge as an engineer too. Everybody got it? Okay. So now I'm going to talk about center of mass equations. So let's say you have point particles. I'm going to write down this. I'm going to say XCM for center of mass. Sometimes I use CM, sometimes I use COM. I don't know why. For some reason, when I code, I use COM, but here I just use CM. All right, it's going to be X1 mass 1 plus X2 mass 2 and here I want to be clear, X's can be plus or minus because they are positions. So when we talk about center of mass, sorry that monitor's in the way a little bit. The X's we mean here are center of mass position vectors. There's an I hat implied. So yet another one of those ones where we don't write the I hat, but it's there. Did that make sense? Okay. Now, maybe you've seen this another way. That's the sum of x sub I, n sub I, from I equals 1 to n, all over the sum of mass sub I from I equals 1 to n. Have you guys used sigma notation before? Just give me a thumbs up, thumbs down. I just have no idea. How many of you have seen sigma notation before? Okay. Okay, good. Oh, question? Okay, good. So yeah. Now here's the deal. What's another way you could write a sum in math? An integral is a sum, right? In some sense. Now let's try and rewrite this in integral notation. It's x dm all over the integral of dm. Now you probably, maybe you don't know what I mean by dm, so I need to clarify that. I'll call this a tiny bit of mass. What units does dm have on it? Kilograms, right? So notice in all of these, the kilogram units are going to drop out. The kilogram units are going to drop out. Over here, the kilogram units are going to drop out. And then I'm just going to put initial and final here, just because I like to do my integrals with limits. So my goal today is to basically understand how to do these calculations. You may have seen them in a math class, but I've got a few tricks that maybe you haven't seen in your math class. Our number one trick, and actually, if you look on page 43, it's going to seem intense, but that's the summary of today's class. So you don't need to understand page 43 now. Hopefully, when we get to the end of class today and we read that summary, that will make sense. In general, I'll summarize that so you don't have to read it. Here's the first thing. When we're trying to find center mass, the easiest way is to just know where it is and not calculate it at all, right? Unless otherwise specified, usually the center of mass of a rod is at the center of the rod. The center of a mass of a disk is usually at the center of the disk. So hopefully, a lot of problems, we don't have to do this calculation. However, what if we get some compound object? Like this, right? I know this seems a little bit crazy. Yeah, I feel like I'm making a movie or something. But right, you could say, where is the center mass of this object? Now you could be saying, man, that integral is going to be horrible, right? No, we don't do an integral. We use this equation. And what I could do is I could break this object into three pieces: rod 1, rod 2, and disk. And then I could say, give me the mass of the disk and the center of mass of that disk. Give me the mass of one of the rods and the center of mass, etc., right? So then we don't have to do integrals. You take objects that you already know about and just use those in this point particle formula. And you say the mass of each object and the center of mass of each object. So that's another way we could do this. And then finally, well, let me show you two more tricks. Three more tricks. Okay, so again, we're just looking at tricks. Here's another one, right? How would you get the center of mass of this? The trick is you can write this as a disk of uniform density and then say it's a positive mass disk and a negative mass squared. And then what you can do is you can use this formula and just plug in a negative mass for the whole. Isn't that cool? Right? Again, avoiding, can you imagine trying to do all these little integrals, 1, 2, and then, I don't want to do integrals on that. Finally, what if you had some structure like this? Now, I don't know if you can see this very well, but what I did here is I just took some aluminum rod and basically, well, I didn't do it. I made the student worker at the time do it, glued all these pieces of aluminum on here. And you could imagine a structure in a building looking like this. So what you could do is you could estimate the density at this end, estimate the density at that end, and make a function for the density and do an integral. We'll explain how to do that when we do the integral parts. So this one, we actually could integrate and get a pretty good approximation for where the center mass is located by giving a function to the density. Finally, what if you have shapes like this, right? So here you would have to talk about the shape of it, and we would have to get that into an integral. So weird shapes, we could actually do this. Again, we're going to focus on the math. Don't forget the why. We care about this because it's useful in real life problems, period, in a lot of applications. Ready to do the math? All right. So let's just do as much as we can. And like I said, I'll send you a video if we don't get to all of it. Know that the review strategy is on page 43. Let's start on page 44, 9.27. Okay, 9.27. I love center mass. I don't know why? It's just fun. Side note, all the math that you do helps in both quantum mechanics and physics 163. So it helps not just in this class, but other classes, and obviously statics and dynamics. It's a pretty useful topic. Okay, we've got 3-point masses shown. Okay. There's something we can learn about this. So even if it seems really easy, let's do it. Get both the X and Y center mass. If you're faster than me, you can just go rushing ahead. I'm going to draw it. 1, 2, 3.
Are we going to use two separate equations?
No, we could do, you could do, so let me, I think I know what you're asking. Let me do this, hold on. So what this means is you could actually do x1, m1, x2, m2, plus x3, m3, as long as you remember to add the m3 in the basement too. So you could go up to x278.
I mean the y values.
Oh, right. So we could do this same exact equation and change all the x's to y's.
So that, yeah.
Yes, absolutely. Yes. Sorry, I didn't understand. Yeah, you're good. All right. So we got a 1 kilogram. I'll call that M1, right? Why don't we call the 1 kilogram 1, the 2 kilogram 2, etc. Over 3 down 2. Sorry if you guys were trying to do the Zoom and then it screwed up. It was just, I got caught in traffic in an accident. not me personally. So what's that? All right, all right. We're looking at page 44, 9.27, center mass. All right, so I'm going to go ahead and do this with you. X center mass is equal to, in this case, X1 is going to be what? What were the increments on the grid? Yeah, okay, we're told these are 20s. And that was centimeters, is that right? Okay, Don's cringing because he would say that's 200 millimeters, but I can't help it. I like centimeters sometimes. So each grid is a 20 centimeter increment there, so you could go by 20s. So it's going to be negative 20 centimeters. Forget about sig figs. And what's mass 1? 1 kilogram? Whoops, yeah. Color coded. Then the next one was mass 2. The x coordinate would be what? 2? Oh, wait, 40. So always check the units. 40 centimeters positive, and that's 2 kilograms. And then the last one is negative 60. Is that right? Okay. That's 3 kilograms. All over, what's the total mass? 1 plus 2 plus 3 is 6 kilograms. So notice the denominator, another way to write it is just total mass. So if you don't want to write M1 plus M2 plus M3, you just plug in the total mass. Before we do the math, maybe you could guess. Where do you think it's going to be relative to the origin? What's your gut? Just have fun with it. Take a guess.
Left and down a bit.
Probably going to be left and down a little bit, right? So let's see if our intuition is correct. When we get this, I got to get a calculator. I don't want to spend all day on it. You can too. Negative 20 plus 80 minus 180. Is that right? Yeah. And then I got to divide by 6. X equals negative 20 centimeters, right? We got to remember the units. And then if we do y center mass, well, let's just worry. Oh, okay, let's do y center mass really quick. All right, so then I'm gonna. Oh, I think I color. All right, so go. Oops, that's 60. 60 centimeters up times 1 kilogram plus, what is this, 2, negative 20 times 2 kilograms. And then finally, plus what, negative 40 times 3 kilograms all over the total mass, which is 6 kilograms. The kilograms are going to drop. What do I get for y center mass? 60 minus 40 minus 120, and divide that by 6. Negative 16.7 or so. Stick in the extra digit because it's a 1. So that means my center of mass location is over 20 and down here. There's our center of mass. And I want to accentuate one interesting fact right away. Nothing up my sleeve here. Is there the same amount of mass above and below the center of mass? Look at the picture. Is the same amount of mass above and below the CM? No. The center of mass, in some sense, is not the center of all the mass in this sense, right? There's not the same amount of mass above and below. It's a mathematical construct. On average, right, the mass is located here. That doesn't mean you have the same amount of mass on either side of the lines. In particular, this is right on the line. We have 3 kilograms over here and 2 on this side and 1 sitting right on the line. We do not have the same amount of mass on each side of the line, up or down. Got it? Never forget that. It turns out later on we'll learn you could almost think about this is where you need to put a support pin, but in this case it doesn't really make sense. So let's go on. All right, good enough. What are the things to notice out of this? That big fact, not the same amount of mass on either side of the line, and also the units of mass drop. So you can use kilograms, grams, whatever. Okay. Ready for something with calculus? Let's try 9.29, page 45. I'm going to erase the board. You read it. We'll get both boards going at it. I know you may have done this in calculus class. I can't help it. We're going to do it right. Okay. Math classes, they never care about units. That's fine for a math class, but it doesn't make sense in the real world. Okay. I can tell your math teachers I said that. Sure. I used to teach that.
Until Krisky said that.
That's right. I can't help it if I want to be useful instead of a useless student. I actually really like math, right? I used to coach the math team here. Old school. Still racing on Zoom, just so you know. Get there. I actually find it easier to do calculus when I have units, right? Because then there's some way to check my math. Okay, let's get into it. Well, this is 9.29. Now we're going to start with 3D calculus, and then I'll explain most problems on the test end up being 1D, but it turns out there's some stuff you can learn in the 3D that you can't. So it's important that we do one 3D, all right? Notice my coordinate system has got we've got I hat out of the page, J hat this way. So it's a non-traditional coordinate system. That's okay, right? Is it right-handed? Let's check. I goes to J goes to K. It's right-handed. I'm doing the wheel of pain. I goes to J goes to K. It works. Now we got this triangular wedge. It's hard for me to draw this well. Kind of close. So this is supposed to be a triangle in 3D. All right. All right. Turns out we're going to use this result all the time, so it's important that we derive it. Now, in this case, I drew a slice of this object right here. Some random spot. trying to show you that's the face of this object here. So imagine I take this triangle and I just slice it right there. The idea is we're going to try and use calculus now, and our calculus equation is, well, actually, all right. We'll write the y center mass here. And again, there are other ways to write this. But if we were doing, say, the y coordinate of the center mass, that's what the integral would look like. And I guess, I don't know if you could tell this, I did what type of slice here? I have a small amount of distance in this dimension, okay? What would be a good name for a small amount of dimension along the y-axis? dy. Can you tell why I wrote a y-centered mass equation now? The trick in all of these problems, this is big picture now, listen up. If you want to do this integral, the trick is you must correctly convert dm into a dy. That's the crux of the problem. Got it? We need to write an expression that relates the mass to the geometry of this particular slice in this particular problem. So our goal is dm must relate to dy to do the math. We need to put some sort of symbols in here, right? So now in this case, do you know any ways that we can relate kilograms to meters? What's that?
Oh, no.
Anything that has both units of kilograms and meters in it that you can think of? True. Volume, anything that has both volume and mass in it? Density. Awesome. So we're going to do in 3D, what's the symbol? Well, this is density, right? Rho. If you don't remember how to draw density, it's like a P, but you start here at the junction, you go around and then down, around and then down. Rho, your density, okay? Somebody help me with the equation for density in terms of mass and volume. Mass divided by volume. For a slice, I have a tiny bit of mass, but I also have a tiny bit of volume. So density would equal dm over dv. Does that make sense? Think about it. This is the mass of my slice, and this term is the volume of slice. If you take mass over volume, you'd better get density, kilograms per meters cubed. So far, so good? What we see is, the real crux is, I need to get dv in terms of dy. Well, let's put in some of our constant parameters here. For this particular wedge, it has height h. So we're told the height of this thing is h. What was is the length of it L?
Yeah.
Okay. And so that means this dimension right here is going to be hard to draw here. That's W. And then that was length. And then we're told total mass is M. All right. How can I get the density? All right, we got to work on this. There's two pieces we got to work on, both the density and dV. Help me with the density. Do we know the total volume?
1/2 HL times W.
1/2 height times length would be the area of this triangle
Times volume.
times the
W.
width, which we call W. Excellent. So notice our density, we could actually rewrite that by flipping the 2 upstairs. For this particular problem is 2m over height, length, width. So far, so good? This is a step sometimes your math teachers may not do where you have to get the density of the object. I don't know. Is that density constant for this problem? Does anything indicate that it's not constant in the problem? Let's read carefully. Oh, wait. A uniform right triangle. When you see the word uniform, that's a fancy way of saying density equals a constant. Got it? There's a lot in this problem. So we're going to get through it and then we'll review it, all right? Because there's just so much in here. Well, think about it. The mass of the entire thing is constant. The height, length, and width of the entire thing are constants. That's not changing. Now, the size of this one particular slice might change, but the size of the entire thing is not changing. Okay with that? How's everybody doing? Thumbs up, thumbs down. Is this about right pace? Okay, all right. Just tell me if I need to slow down or speed up. All right, now in this case, we've got one piece of the puzzle. Let's get dV. That's the hard part. And then just so I have some room, I'm going to rewrite these words just a little bit over here, just to give myself a few more inches. Any guesses on how we approach that? In particular, if I choose a different slice, would I have the same volume or a different volume? That's what I need to know right now. If I move to a different spot, would I have the same volume or not? It's going to be different. So do you agree the volume has to be some function? Okay, so how about I write it like this? dV will equal height of slice, width of slice, times length of slice. Do you agree with that statement? It's basically some sort of a rectangle. Two of those things are constants. Which two?
Length and width.
Length and width. So in this case, you could argue like what I would say the length is dy. Do you right? And you could say the width is w. Now maybe somebody else would say, oh no, I think it's the other way, but whatever. Basically, length and width, only the height is changing. So let's rewrite this. So my claim is all we have to do is get the function for the height. And we're golden. Well, do you recognize this type of function for the height? What type of function does that look like? Does it look like an exponential, a cosine, a parabola, a line? Does anybody know any equations for a line? Y equals mx plus b. I like that kind of, and I want to change one aspect of it. Do you agree we already have m in our problem? So I'm just going to say slope x plus intercept so we don't have that confusion. You know what I'm saying? You're absolutely right. Everybody says y equals mx plus b. But what I want to do is I want to say y equals slope x plus intercept. That way I don't have to worry about, is that m mass or is that m slope? That's all I'm saying. There's no rules here. What's the slope?
Negative h over L.
So it goes down h as you go positive L. Excellent. Nice. So y is equal to negative h over L. If the rise is negative h, and then I better be careful here. I should be very careful. I made a mistake. It has to do with the coordinate system. Strictly speaking, we said y is along the to the right direction. You agree? So what did we call this direction here? K hat, so that's a z, or maybe I should call it height of slice. This is, so I'm going to say in this case, I'm going to say the height of my slice depends on the y coordinate. You see how this is a little bit tricky? Normally we say y equals mx plus b, but in this case we're saying z equals slope y plus intercept. I'm going to pause there, make sure you digest that. It's just from me rotating the coordinate system. In this case, the height is basically a z coordinate. And it depends on the y coordinate as you travel. What's the intercept?
Positive h.
H. Oh, you're doing horizontal. I meant the vertical intercept too. Sorry. Got it? So what's our dv? The height of the slice, oh my gosh, this is kind of ugly. I'm going to factor out an h, I guess. And I'm going to rearrange it 1 minus y over L. Take a second to see if you agree with this after I get it done. It should have a w dy in it, and then the height of the slice is this screwball formula, and all I did was factor out an h, and then shift it to 1 minus y over L. Is everybody okay with that? It's a little different than your math class where they always put the point of the triangle, and they said, well, why don't I just use similar triangles? Because it won't work for this problem. Similar triangles only works for one special case. Drives me nuts. Your math teachers teach you that way. Send them that video. All right. Sorry, I'm raging on math teachers right now. Okay. Whatever. Are you guys ready to do the math here and see what happens? All right.
I have one.
Oh, Dom, go for it.
The ability to model linear equations is critical. They show up again and again and again. You can't do y equals mx plus b type equations and numbers. You're going to have a tough time doing problems.
So many.
The equations we use are not usually very hard, but systems like this need to be really good at that.
I totally agree. I hammer this every class too. So like being able to identify a linear function in a problem and make your model incorporate a correct linear equation for the line you see in a picture is a big deal. Here was another case that I was talking about, right? Even though this is only approximately linearly changing, the results from modeling even this kind of discrete thing as a linear function are huge, right? You get a very good result in the real world. Like what if you're trying to find the center of mass for a staircase to make sure the building doesn't have inappropriate supporting structures? Geez, you better get this right. All right, anyway, yeah, I totally agree with Dom on that. Absolutely, linear, over and over and over. Be expert at it. Anything else on that, Dom, or is that the main thing? I totally, yeah. All right, ready to do the math? So I'm just going to put all the pieces over here. Our equation was y center mass is equal to from initial to final of y dm all over the integral of dm from initial to final. We found that dm was rho dv. That was just rearranging the density equation. So in this case, dm is equal to rho, and our crazy function for dv, HW, drank my milkshake. What movie is that from? No, it's a string. HW, this is my son HW. I'm an oil man. No. There will be blood. That's a HW reference. The kid in that movie was named HW. All right, moving on. What else do we have? We have DM. What are our limits in this case? Right?
0 to L.
0 to L, because remember, we're looking at this thing here. This was y equals 0. This is y equals L. Right? So let's plug all this junk in. DM is So notice there's an extra y in the numerator term. You could check the units at the end to make sure you didn't forget that. Then our limits should be 0 to L. 0 to L. Woo! Looks ugly, right? Is anything a constant? What is constant in here? Density is a constant. What else?
H and W.
HW is also a constant. Look, it's in both terms. Do you agree it's going to pull out and then you can cancel it? So it turns out we didn't even need the density for this particular equation. Side note, what's the answer to the bottom integral?
Y.
I'll give you a hint. Look at it this way. What's the answer?
Yeah.
The mass. What is on the bottom of the center mass formula? Total mass, right? You remember that? It's always xi, mi, plus, blah, blah, all over total mass. So here's the trick. Some students see this and say, well, shit, that's just m, total mass. If you do that, your constants might not drop out. Do you see it? So it's 6 of one, half a dozen of the other. If you plug in the basement is total mass because that's a known quantity, then you need to compute the density. Otherwise, you can write both terms in terms of the density, and if it's a uniform density, it just drops out. So I don't like doing this, but I'm just going to cross these terms out. Are you okay with that? Again, it's not right to cancel them when they're inside the integrals normally. But because they're all constant, they pull out and then cancel. Is everybody okay with that? Bad person. I'm lazy and I'm running out of board space. Rewrite. What could I do before doing the integral to see if I'm on the right path and make sure I haven't made any mistakes? What's something I could check? The units. What are the units on this side? Meters, centimeters, some kind of distance, right? So that the units, careful. We know this should be meters, right? I'm going to write the whole word just so it's not ambiguous. What are the units on this? Meters. Meters squared over meters is meters. Meters minus meters is meters. It's a y, it's a meter. So what do I have on top? Meters squared, right? What do I have on the bottom? No units. No units. No units. Meters. Are the units going to work?
Yes.
Sweet. So this, you don't have to do this, but you can check the units at an intermediate step to make sure you didn't accidentally forget to cancel something. You know what I'm saying? Because this is pretty complicated looking to me. All right, now I'm going to keep going. You're probably like, why didn't I just do the math? Yours are driving me nuts. True enough. We don't. All right. When I integrate this, what do I get from the first term? Y squared over 2. Evaluated at 0 and L minus this next term.
1 over 3L y cubed.
Y cubed over 3L. Evaluated at 0 and L. And the next term, oh, whoops, the basement. The first term gives me
Y.
Y. Not a good joke, but it was an attempt. Sorry, dude. You gotta have fun, right? And this one's gonna be what? Y squared over 2L. Always check the zero limit. Always check the zero limit. Right? In this case, do you agree all of the zero limits are 0? I kind of did a lot here. Does anybody, is everybody thumbs up, thumbs down if you're okay on the integration? I try not to mess with you too much. We stick mainly to polynomials, right? But you could do this with cosines and sines and wolf them out if you need to. All right, so basically we can rewrite this everywhere except just replace the y's with l's in this special case only. I'll get out of the way. Just trying to make sure I stay on the screen real quick. Am I still on, Jules? Thanks. All right. Wait, what did I screw up? Does everybody see what I missed?
Wouldn't the second L on top be squared?
See that L there? Yeah, I forgot that L in the basement. Yep, which would make it an L squared. Yep. So notice checking the units. We know it should have been right. So then I'm like, wait a minute, something's wrong. Okay, cool, we caught it. So now I can cancel this L and make that an L squared. I can cancel this L and make that just an L to the 1. What is left in the numerator? What do we get left here? L squared, or wait, we have L squared times 1/2 minus 1/3 all over L times 1 minus 1/2. What do you get on the top? Well, do you agree one of the L, we can cancel another L. That's cool. There's our units, L times a dimensionless quantity. What's 1/2 minus 1/3?
1/6.
Yeah, because you got a 3 over 3 and a 2 over 2. So that's 3/6 minus 2/6 equals 1/6. On the bottom, we have 1/2 1/3 L. Is that on there, Jules?
Yeah.
Okay, cool. What do you think of it? Who wants to do this problem again? No one, right? So memorize this frickin' answer for the rest of your life. You know a triangle's center mass is 1/3 from the fat end. Think about it. 1/3 from the fat end, boom. 1/3 from the fat end, the center mass is somewhere on that line. Well, wait a minute. It's triangular here. Now we're talking about right triangles. I'll clarify that there. Where's the center mass going up? Is it 2/3 from the fat end?
Wouldn't it be 1/3 as well?
It's 1/3 from the fat end. Here's the fat end. Isn't that beautiful? Now we know the center mass for right triangles is 1/3 from the fat end. For the rest of your life, we never have to do that calculus anymore. So I guess this is 1/3 of its height. What do you think about that? We're going to use that all the time. Triangles, squares, circles, rectangles, most objects we can make. You throw in a rod here or there, we can make a lot of stuff and not have to do a ton of calculus. Anything you want to say, Jules, Dom? Oh, wait, question.
Yeah, I just have a question. That is, does the center of mass change depending on what part of the earth you're standing on?
Strictly speaking, sure, right? And this is why I didn't go into this, but do you agree as you go up in altitude, the gravitational force changes, right? When you get farther from Earth, gravity gets weaker.
Yes.
It doesn't just shut off. So strictly speaking, right? If you had a big enough object, say 1,000 miles tall, right? That would, right? We would, this center of mass would not be the same as where the gravitational force is acting. That's the subtle difference between the center of mass and the center of gravity calculation. So, but for the most part, we're going to ignore that because for the most part, we're not dealing with objects that are hundreds of meters tall that might have, and even then, that's only going to be a small change. I don't know if I addressed your question. You want to say it again?
Well, it was not about the height of which the object is at, but rather the place on Earth, for instance.
Oh, and so similarly, if
Yeah.
we were doing experiments, so, right, we're going to assume the center mass is the same, whether you're on top of Mount Everest or in the Marianas Trench.
Okay.
Right? So, yeah, and that's because we're assuming, and that's why I brought up the height. It's because unless your objects are really, really big, right, that's not going to matter, right? The mass should be centered regardless of what place you're in. Did you notice? Because the gravitational force does fluctuate on Earth in like the third sig figs. So, is that enough on that? We can talk more after class too, if I'm not getting your question right.
So does the center of mass change on different planets?
No.
No?
Does your mass change when you go to the moon?
No.
Does your weight change? Yeah, so your mass is just your stuff, your molecules, right? And so the center of your well, I guess it might change, right? Because you might be really, really hungry and you might like basically be on a diet. But assuming you had the same amount of food supply and you don't lose weight or something, I would assume your center of mass is still right about there.
Does the object change geometry?
Yes, that's a good
Does
way to
the
put it.
object change geometry? Yes or no?
No.
Does the material that it's made out of change? And materials with density, so it's mass. Your mass does not change. How it's distributed does not change. So the center of mass is the same wherever you are in the universe. The complication comes in when you think about center of gravity. That's where the effective weight of a system acts. But most systems are very small. And so the gravitational force on any point is any little dm, where all the dm's are the same, is going to be exactly the same for that location. And if you move it to the top of Mount Everest, they're all going to be attracted the same, different values, but all of them will be attracted the same.
Unless you do something like this, where you change the orientation of the pieces of the object, we do not expect the center of mass to change, right? If you bring this to Mars, it's basically the same material and the same orientation, ignoring any effects from slightly reduced gravity, maybe reducing stresses and changing the bulk. But if you change shape, so another fun one, right? You could talk about this, right? If you had an object like this and it swings, right? We could talk about the center of mass changing, and we could actually do calculations on that to understand the rotation rate. So we do plan to approach this where the center of mass is maybe changing, but most of the time that's like, we're going to try to avoid deformable systems in this class. A last thing I'll mention about it, did you see G anywhere in this calculation? No. So we're ignoring, right, where you're at on the planet or which planet you're on, because there's no G in here. So again, we're assuming when you change places, the object stays basically the same shape. Obviously, my center mass is changing when I move, right? But it's pretty amazing dance right there. All right. Oh, geez. Okay, so one last bit on this. Good questions, really good questions. Look at this right here, right? Strictly speaking, We have not specified the center mass fully. We've only specified its, what was this axis? Y. And then up here was Z axis. This direction was X. So if I wanted to write the center of mass in coordinate form, what is the X coordinate of the center of mass for this triangle?
1/3 W.
No. It's not changing in the W, in the X direction, right? It's just halfway. No. Where is it located on the coordinates? Let's go back to the better picture here. Hold on. So it's triangular, and so we have to deal with the triangularness in both the Z direction and the X direction, right? But what about, the Z direction and the Y direction? I don't know what I just said anymore. But in this case, as we're going into the page, is that positive I hat or negative I hat according to this coordinate system?
Negative.
And then do you agree this object is symmetrical as we go into the page? So it should be halfway, and then a third of the way, and then a third of the way up. Right? So this distance here should just be W over 2. Did that make sense why that one's not a third? Right? It's not triangular in this. Look, it's got a kind of this square face or rectangular face. It's hard to tell if H and W are exactly the same dimension here in this picture. Right? But it should just be halfway into the page, halfway through the thickness of the plate. Right? Think about it like this. I know this isn't a very good, sorry about that. I know this isn't a very good representation of this triangle, right? But the idea is on this axis, there's no reason to think it's not exactly in the middle, right? On this axis, it's complicated. It's 1/3 here, it's 1/3 up, but it's exactly halfway on that one. Good? So finally, we can rewrite this all. The X coordinate would be what? Negative W over 2, because it's W over 2 into the page. The Y coordinate would be 1/3 L, and the Z coordinate would be 1/3 of the height. That's the location of the COM. What do you think on that? I spent a long time on that one. It turns out we can now basically do any problem we want with some shortcuts. We're going to take a break and then we'll come back and I'll go through the summary and we'll just do as many problems as we can stay in. I showed you this complicated way, even though these canceled out. This is the last thing. In some problems, density is not constant. Here's that example right here. The density of this is not constant because as you go across, you're adding different amounts of material. So you could model this as a rod whose density is increasing. Or maybe you have a cable. And if you have a cable like this, cable might look like a cylinder, you could have some overwinding, right? And then as you get towards one end, you could overwind more rapidly. And you could have a density that varies from one end to the other. Or we could talk about electron wave functions, and they have a density that varies throughout space. There's lots of cases where density is not constant. If it's not constant, I'll give you an equation, you plug it in, and you do the math, same old, same old. That's the only difference if it's non-uniform. Go ahead.
So the shape of it isn't necessarily relevant. What matters is whether it's increasing or decreasing in density and mass. Because that rod there has an increasing as it winds more, but it's not getting taller and taller.
Right. So basically, in most problems, we're either going to account for the change of shape of the object or account for the change in density of the object right here. And that's why we oftentimes have to do calculus. Is even if either the density or the shape is changing, then we got to do something like this. Cool? And then hopefully we can just memorize the rest of it. Let's take that break. It's been a long one. So what do I got up there? We'll take a 10-minute break here.
On this clock, I see 12:17. All right. All right, about that time. We're gonna get back into it, those of you out there, just letting you know. All right, so I want to look at the strategy on page 43 now. So I want to look at this. Oh, that was it. Sorry, Jules, my bad. It was, okay. I want to look at the strategy on page 43 really quick. Basically, in theory, we've done just barely enough examples, but we're going to try and do more if we can here. That said, I want to do the summary. If you're looking for center of mass, the easiest way is just to know the answer or memorize, right? In particular, usually it's right at the center, or for a triangle, 1/3 from fat end. Or if you had a circle or a rectangle, right, it's right at the center. So a lot of problems, that's enough to get the job done. So why would we do any math if we don't have to? Okay.
Because you
Step
love
two,
math.
what's that?
Because you love math.
Yeah, true. Okay. So you could do it. All right. So we could take an object and build it up out of known shapes. Let me give you an example then. Look at this thing. Imagine you're a civil engineer and you were going to make some kind of a concrete balcony or something, right? And maybe it has to be some weird artistic shape like this. Hopefully you see that you can split this into some rectangle and triangle type shapes, right? And we'll do that problem in a minute if we have time here. But so what you can do is you can take an object, and because I know how we're going to do it in the next problem, I'm actually going to split this into 3 shapes. So there would be a center of mass right there. There'd be a center of mass right here. And where would the center of mass be for this piece? 1/3 from the fat end, so maybe about right there, something like that, right? And then what you could do is you could say X center of mass equals X1 M1 plus X2 M2 plus X3 M3, and then divide this all by the total mass, which would be, trust me, there's a reason to write it out. Right? Now, what happens here is sometimes we need to rewrite the masses in terms of density to simplify work. So it turns out if we rewrite the masses in terms of density, just hang on here for a second, give me your eyeballs for a sec. I promise to give you plenty of time to write it. This is also written in there, but if every term has the same density, you see the density dropping out? So sometimes the trick is, I don't know what the density is. I don't know the density of concrete off the top of my head or aluminum or whatever I'm going to do, but I could plug in density, and as long as it's uniform, it's going to drop out. And that allows you to rewrite the mass in terms of the areas and volumes, etc. You see that? So you could take something that's a geometric shape and rewrite the mass in terms of the areas and get those areas involved here. So far, so good? Another thing that you can do is this one, right? When you have something like this, you can rewrite that, and I'll just show you this equation now. right? If you had this, I should be careful. In every problem, there's supposed to be a coordinate system too, but whatever. Right? If you don't have a coordinate system, how are you going to know the numbers for X? Agreed? So usually there's got to be a coordinate system somewhere. Let's just assume the coordinate system is right here for right now. I probably should have written that in there. Have a coordinate system. Right? This is equal to the solid disk minus a solid square. Right? So if you take a solid disk here, what you could do is then you could say, and actually let's make this red so it stands out. We could say, oh, this one has a center of mass right in its center. This square has a center of mass right in its center. And then what we could do is we could say, just give me a sec, X center of mass is equal to, the idea is treat this like a negative mass, right? Because we're subtracting that piece. So then we could say it's X1 mass 1, and that's the entire solid disk, minus X2 M2. Notice it's a minus sign because it's like it's taken away, over mass 1 minus M2. Does that make any sense? And now I'll pause to make sure you're caught up. This is all bullet 2. So if we can't just memorize the answer, see if you could build it up or subtract it out and do the center mass that way. Does that make any sense? Quick question for fun. You can kind of see the quadrants here, right? Going by this. Where's the center of mass? In which quadrant? The third. If you take away mass here, that shifts the center over here somewhere. That's kind of fun, right? There's less mass up here. It's got to shift the center mass the opposite way when you cut a hole. That's kind of for your intuition. And then the third one, do calculus. Only if you have to. So that's for wild shapes or non-uniform density. That's typically when we tend to do these problems. Now I want to talk about density a little bit more, just to make sure you understand what a physicist thinks about density. Any questions on this board? Okay. Now, this is kind of important, and it shows up periodically. I want to look at, let's do this. Well, how about this? We'll get the slinky out. That'll give you a chance to show it. Depending on how you're going to do your math, you may treat objects as one-dimensional, two-dimensional, or three-dimensional. And I want to talk to you about how density, like here's a slinky, right? Do you agree that it's more dense at the bottom than it is at the top? You could actually, there's more rings per inch down here than there are rings per inch up there. So you could actually treat this as a non-uniform density, one-dimensional object. Right? So in 1D, I have the right board? Yeah. Sometimes we use a term called linear mass density. The symbol used is oftentimes mu or lambda. We're starting to reuse Greek letters. It's happening, folks. So sometimes we use the symbol mu, sometimes we use the symbol lambda. The units are kilograms per meter. And what happens here is typically this leads to an equation that looks like dm equals lambda dx, or dm equals mu ds, where you could use an arc length. Okay? It's important that you know this because if a calculus problem shows up on your test, more than likely it's going to be a 1D problem. Okay? Check the units though. Let's just do a quick unit check. What are the units of mass? dm? Kilograms, meters, kilograms per meter. So if you have some object that's basically like a rod, or like I said here, you could treat this as a 1D object, right? It's pretty much a rod. So you could say, well, rather than worrying about the thickness and the width and the height and all that stuff, let's just call this a rod, and we'll just say how many kilograms per meter as you go along. Got it? It's a practical thing to do. If you ever buy space in a moving truck, you usually buy space per foot. And what they're doing is, right, you've got this huge moving truck. And what you do is if you buy space in a truck, you buy space on the foot. And so they charge you based on the foot, even though you get a volume of space, right? If they know how far from this wall to out here you go, they know how much volume you get. It's easier for them to charge by the foot, even though you're technically getting a volume out of the deal. Same kind of principle. All right. Well, you already know volume mass density. What's the symbol for that in a physics class? Rho, rho, rho. What are the units? Meter cubed, because it's a volume. And what do you get when you do dm in your calculus? We get rho dv, a volume. Right? Again, the kilograms per meter cubed work out. So if you want to slice your object up into volumes, you need to use a volume density. If you want to slice it up into 1D chunks, we would use a linear mass density. G, what's the one in between? There's got to be some kind of area mass density. The symbol for that, we're going to use sigma. Draw the circle, then the line flat. It's not delta. Delta's the cherry bomb. It's sigma. Maybe I'll label these just so you know. That's mu. This is lambda. This is sigma. This is rho. Just for clarity. What are the units going to be? Kilograms per meter squared, which means our dm's in our calculus equations are going to equal sigma times d area, a small amount of area. And just finishing this out, we have kilograms per meter squared times meter squared equals kilograms. Now to be clear, let me give you an example of that. In a lot of problems, right, the thickness of something is negligible and uniform. So this is our triangle that we just did, right? It's a 3D triangle. But do you remember in that calculation, both the numerator and the denominator had a W in it? Do you remember that? And the W's could have canceled out. We could have just treated this as how many kilograms per square inch and just kind of ignored the thickness, assuming the thickness is constant. So if the thickness is constant for a shape, we could talk about kilograms per meter squared, and that's what I'm talking about here. Is that okay? So all that is summarized at the bottom of page 43. Got it? Okay. So use the units to help you figure things out. Like if you're trying to figure out a density and you know an area and a mass, you can get a sigma by doing mass over area instead of doing mass over volume. I hope that's clear. Ready to do more practice? No? All right, that's cool. All right. Which problems would you like to try? I'll leave it up to you, and I'm going to focus over here. Do you want to do weirdo shapes that we put together, or do you want to do calculus? What do you want to do first? Just, I'll say it this way. How many want to do something from the number 2 column?
No.
What's that? You want to do one?
Yeah.
Anybody else? Oh, okay. All right, I guess we'll do that. I don't know. Is that cool? Or how many of you would rather do calculus? Okay, that is clear. We're going to do it. You want to do one with the hole, or which one of these two do you want to do? You want to do the blue one or the silver one? Which one looks like more fun? Silver, let's do it. Okay, flip the page. Look at page 46, 9.31. 9.31. We're going to be doing this in lab tomorrow with calculus on the computer, by the way. So most people find tomorrow's lab to be extremely difficult. So if you get a chance, actually watch the videos before lab.
Is it a coding lab?
It's a coding lab. It's pretty cool. And because it's a coding lab, if you have a good setup at home, I'm not offended if you want to do it at home and zoom it in when you have questions. You know what I mean? There's training videos, and some people are passionate about coding. Are you or not?
I need coding to do what I want to do, so.
So it's not bad to learn how for loops and while loops work. Yeah, exactly. I think it's fun, but I'm also kind of weird. All right, 9.31. Let's do that.
Which yours?
Yo.
There's a question that we just bring at the end. That is there such thing as an object with a universal center of mass or center of gravity?
A sphere? Maybe as you rotate it, the center mass is always in the same spot. I don't know. That's what comes to my mind, but that's probably not what you're thinking about. I mean, yeah, so I mean, if you throw an object, its center mass moves with the object. So there's a case where no matter what you do, if you're going to move the, yeah, so I'm not sure. We could discuss it more in a minute. Let's get into 931 though. A, B, C, D. A, B, C, D. Okay, so we're going to use our coordinate system right at the center. So again, notice you usually have to have a coordinate system to make sense of these problems. We're told in this problem, this dimension is B. This dimension is A. This dimension is C. This dimension is D. And then I like to have a little bit of shading in here, just so I can tell what the object is and what's just lines. And then for me, I mean, I see two logical ways to proceed. You could split this into two shapes, a rectangle and a triangle. But for me, because this is already kind of split up. I think it's easier to split it into 3, and it's certainly not that much extra work to split it into 3. If anything, I don't have to think as much on where the center mass is located. So I'm going to split this into 3 shapes. In particular, there's this one, which I'm going to call number 1. There's this one down here. 2 rectangles. I'm going to call that number 2. Got a triangle. I'm going to split it into 3 shapes. And when I do this, I'm going to write my, what are we trying to figure out here? Get the x coordinate of the center of mass. And again, I was trying to imagine something that might be practical, right? Maybe you're trying to adjust the sizes of these rectangles so that the center of mass is right here, so you know where to put a support column in a design project. So again, we're trying to, by analyzing this thing algebraically, we can then adjust the design and figure out, oh, okay, whatever, maybe we need it here or here, and we can, anyways, all right. Let's do it. X1, M1. X2, M2. X3, M3. We got an M3. Got an M2. Got an M1. And we're trying to get the X coordinate of the center mass. We're going to add those on top, add those on bottom. Notice total mass on bottom. Okay. In this case, the first step is I want to rewrite the masses in terms of the density. I'm going to ask you, when you look at this shape, what do you think? Would you want to treat this as a 1D, 2D, or 3D object? What's that?
1D.
1D is tricky, right? Because it's changing differently over here than over here. So I wouldn't want to do 1D.
2D.
I would say 2D is probably the easiest, because then it's easier to rewrite the mass in terms of this area. You might be able to do it as a 1D, but I'm not sure. That's too confusing for me. I'd have to do a lot of thinking. That doesn't mean it's not doable that way. It's just hard for me. Okay, so let's try it. It might actually be really easy in 1D if you see it right. We can talk about it afterwards. I'm going to go with 2D just because I see it in 2D right now. So my density is going to be sigma. I don't know what sigma is, but I can get sigma times area 1, right? In particular, what's the area of this one? What's the area of object 1 up here? AC. Now, to be clear, here sigma has units of kilograms per meter squared. It's all made out of the same piece of wood. I'm assuming the density is approximately uniform. It's not perfect, right? It's only approximately uniform. But all of these terms are going to have that same sigma. They all have the same kilograms per meter squared. So eventually, even though I don't know what it is, it should cancel out. That's why I'm introducing this unknown parameter. Does that make sense? What am I going to write for mass 2? Somebody. Take a guess. It's okay to be wrong. Sigma area 2. Well, what's the area of object 2 then? BC. What's mass 3 going to be? Somebody else?
Sigma area 3.
That's it. What's the area for object 3?
1/2 AD.
Got it? At this point, now we got to get the x's. Now here, what do I mean by x1? I mean center of mass of object 1. So look at object 1 And give me, and I guess I should say it's the horizontal, because we're doing X, right? So in this case, I'm assuming this is the X axis, and we're back to a normal one where that's the Y axis. Sorry about that. What is X1? What is the horizontal center mass for object 1? No, close. Negative 1/2 C, right? Do you agree? Based on this choice of coordinate system. So that's what you gotta watch your minus signs. Good job. So negative C over 2. All right, all right. So what's X2? That's gonna equal horizont COM object 2. What's that gonna be? Somebody else. I want the horizontal component of this object's center mass. Negative C over 2. It's again right in the center, right? The center mass of this is right in its center. The center of mass of this is right in its center. So it's, again, negative C over 2. Did that make sense? So all I'm trying to do is get the pieces to plug into the equation. Who's feeling brave? X3. I want the horizontal COM object 3. 1/3 D. I think that's it. D over 3. Remember, for a triangle, it's 1/3 from the fat end this way, 1/3 from the fat end that way. So somewhere right around in there. 1/3 from the fat end. Nice. At this point, you have everything you need to plug it in. That's the hard part, getting the setup. You feel okay on that? The answer is there. I would like to kind of blow past this, but let's see. For me, it's like that was the hard part. The rest is just algebra. If it's drawn to scale, where do you think the center mass is? If this is drawn to scale, do you think you get a positive or a negative number for the center of mass? What's that?
Probably possible.
Which side of where is there more mass? To the right of the origin or to the left of the origin? Probably to the left, because there's these two pieces. So I would expect a negative number if we actually have real numbers to plug in. Why am I telling you this? That's a way to check your answers. It's just to kind of think about it and say, would it be positive or negative? Okay, what else? Okay, so look at part C. We're not going to do it, but that kind of gives you an idea of how you might analyze this. Suppose an architect wants the same type of shape, but she wants the X center mass to be above the origin to be, so you're free to adjust only the parameter D. So basically you could adjust the parameter D in your equation to make sure the center mass ends up at the edge of the building where it would be easy to put a support post. Does that make sense how or why you might do this algebraically? If you really cared, you could do it. Should we move on? 2 more? Let's do 2 more. All right. You want to try a non-uniform one since we haven't done one of those yet? Let's try it. Look at 9.34. 9.34. Let me switch the cameras. It's this one. We've got this object, right? Hey, student, chop these things up. I had them. You probably can't see them here, but literally, I chopped up a chunk like the left end, and I chopped up a chunk like the right end, and I literally got the mass per centimeter. I figured out the densities of these 2 chunks at the left and right end, and we could use this information to get a function for the density and do a true non-uniform density problem. So in this case, let me draw it. So we've got this object here. And it's got some aluminum overlaid on top. And the idea is it's a rod. That's a 1D shape. So what I did is I found lambda at the left end was 3.62 grams per centimeter. Lambda of the right end was 13.14 grams per centimeter. And the length of the rod is 50.0 centimeters. Okay. Now, that's the numbers from part C. We're going to try and set this thing up algebraically in terms of the symbols like this, because that's what I'm more likely to put on a test. On a test, I usually don't give you numbers here. I make you figure this out. So part A, it says determine density of the rod. In particular, we want a density function for rod, assuming it varies linearly. I want a density function. Any ideas? Something varies linearly. What do you usually write? Remember what Dom and I were harping on earlier?
X equals y equals mx plus
Y equals mx plus b. Only now we're not talking about the function y varying. What is changing as you move linearly? What is not the y coordinate, but
yes.
the density is a function. So lambda is some function of x. Does that make sense? Lambda is a function of x. Well, help me get there. Any ideas? In particular, how can I write the density in terms of lambda L and lambda right? Maybe it would help if I viewed this thing with a plot. On this axis, I want x. Up here, I want lambda as a function of x. Well, it's supposed to be linear. Do you think it's going to be sloped upwards or sloped downwards for this picture? Is the density going up or down? What's it look like?
Up.
Up. Is the density 0 at the left end? Or is it non-zero? So it's probably going to look like some non-zero value sloping up. Agreed? How far do I go in the x direction? How far does the rod go in the x direction?
13 point.
L is the distance it goes. How far is how? No, you're right. That's the value up here, right? So that's lambda right. And this is going to be lambda left. And this is going to be L. Does that make sense? You're right. It goes up to 13.14. If it helps, we can look at the numbers here, right? It goes from 3.62, and this goes up to 13.14, right? So sometimes seeing the numbers kind of helps you visualize it, right? Well, give me the function for this line in terms of the variables. I'm not going to write the of x because it pisses me off today. Lambda equals, what's the function? Slope x plus intercept. Agreed? What's the slope? Well, what's the rise? Lambda L minus lambda right is the rise. It rises. Whoops, no, it's not.
R minus L.
R minus L
Over L.
over L. What's the intercept?
Lambda L.
How could you check this equation?
True. Good. It works. What else? There's a quick check. I know you guys are probably bored out of your gourd, but listen to me now. Really, please, please, please. Every time you write one of these stupid equations, it's easy to screw it up, but it's also easy to check. If you plug in x equals 0, do you get the right answer? If you plug in x equals L, do you also get the right answer? Yes, it's working. If you check 2 points on a line and they both match, you must have gotten it correct. So if you just do that simple check before you do any math with it, wait, when I plug in the 2 endpoints, do I get the right answers? I wrote it down correctly. You see what I'm saying? That helps you check if you flip something, or like I would have caught it if I flipped those or whatever. Good on that? So now, how do I get the center mass? Okay. X center mass is equal to the integral of x dm over the integral of dm, right? We could stick the entire rod out of balance, but we don't need to. dm for a one-dimensional object is going to be lambda dx. So to be clear, we're going to change all of the dm's in the problem to lambda dx's because it's a 1D problem. And then there's no x in the basement, so that's just a lambda dx. Circle that one too. What do you think? What are the limits of integration? 0 to L. The smallest value for the x integral is 0. The largest is, oh geez, this is kind of messy, isn't it? That's x equals L. Sorry, there's just a lot going on here. Is that more clear? Yeah, this is x equals 0. So that's why our limits go from 0 to L. Once again, the joy of a linear function. We can integrate it, turn the crank, you got it. The setup is the hard part, in my opinion. You guys want to keep working it or not? You've got this, remember, you've got full solutions already written in the book if you want to do it at home, right? I wouldn't leave you to this if I didn't know the solution was already written. So you can check it at home. What's that? Yeah, so let's do one more step just to make sure, right? So we know what to plug in. So just right it. So you can't forget this extra x, right? Otherwise the units don't work out. So it's going to be x times, I'll get out of the way, that would be what the numerator looks like. Is that what you were wondering? Yep, you were right. What's that?
Isn't there also another x in the inside? The lambda?
Oh, I missed that x. You're right there. Absolutely. So there should be an x. Yep, thank you for catching that. Sorry, there's an x right there. And again, we would have caught that if we had checked the units. So you can see, right, I've been doing this a long time and I still make the same mistakes you do. So having those ways to check your work matters more than trying to be perfect every time. Because if you can check your work, you can usually recover from any mistakes. Well, that seems strange, but checking your work often is a good idea. Knowing how to take a real-life problem and shove it into a linear equation is also useful.
I can't stress that enough. Dom and I beat that into you. Enough said. What do you think? And then from there, you could, right, we could plug in numbers now, or we could do the integral and then plug in the numbers afterwards. I think that's the better way to do it. How could we check it? Let's say we got the answer. And what did I write the answer? I did the number. I found 29.7. Out of all this, I've got 29.7 centimeters when I plugged in all the values. If that's the case, does that make sense? What do you think? If this was a uniform rod, where would the center of mass be?
Center.
25. Now, when you look at it, does it make sense that it got shifted over to 29? Should be a little bit to the right because this end's a little heavier, right? How could I verify this experimentally?
Stick your finger up the center.
Yeah, and so because I shake too much, there's all those quaaludes. Actually, just coffee. I've got a nail, right? And so let's see here. Right? Okay, so in this case, oh, look, this is about 30 centimeters long. Okay, so hopefully, all right, should be pretty close to there. It's about 30 centimeters. Obviously, there's a little bit of an error there, but so we see that here we have a problem. This is clearly not a linearly variant function. There's actual steps here. But we could see that by modeling problems with a linear function, you get really freaking close. And this makes sense. Which side has more mass? What's that? How many think this side has more mass? Raise your hands. How many think that side has more mass? Is the center of mass have equal mass on either side?
Yeah.
No,
Oh, wait.
almost never. Every single problem today, remember? Yeah, what matters is the gravitational torque is balanced, right? And so I think, yeah, I don't know.
Okay, yeah, that makes sense.
Yeah, remember, so we don't, it doesn't split the mass in half. Because this mass is centered closer, you probably have more mass on this side because you have, we haven't talked about torque, but you have a shorter lever arm, so you need more mg on this side. We could discuss that in chapter 10. But basically, yeah, the torques have to balance here, and as a result, we're probably going to need a little bit more mg on this side to balance this longer distance away. Cool? In general, do not assume you have the same. If we wanted to figure out the mass on each side, how could it be done? I want the mass on this side. How could I do it? I don't want to chop this thing up and, right?
Would it be by determining the torque? Or do we just completely avoid that and just calculate by what the 2/3?
Okay, how could we solve for it? How could we solve, what equation could I do? Okay, yeah, kind of. Let me do this. I'm just going to make some space. Do you agree the integral of dm is mass? Right? If I want to get the mass on the left side, I could go from 0 to 29.7 centimeters and get it, right? And we know some stupid function. Done. Cool. All right. What do you think? Feeling pretty good? Here's a weird one, since we got it. Now notice this is super unstable, which I like. This is a fun one. In your problem, take a look at 9.36 really quick.
9.36. The idea is you have a solid disc and you have these two rods. And my question was, how far do you have to separate these rods to make it balance? Right on the edge, right? And so I think that's what we're trying to do. But we're trying to balance it on the inside edge like this. So the idea is, as I spread these rods out, you could balance this thing, which is what this stupid bird is all semester long. You remember this? You see it? Isn't that dumb? I like to do this with a 50-cent piece and 2 forks. So next time you're got a 50-cent piece and a couple of forks, you can do that. But here's a fun one. This kind of reminds me of a tightrope walker. A tightrope walker usually has a very long pole, right? And it's flexible. Why is that? What happens when you have this rod, you're carrying a rod and it's really long and then the ends dip really low. What happens to your center of mass? It goes down, right? Also, by having a very long pole, you're going to have a lot of moment of inertia, another topic from chapter 10. So that's the next thing we go into. We'll do that next week. But if you have a large moment of inertia, it takes more time for you to rotate, so you have more time to react before you fall to your death. Because I never use a net. Yeah. You good? Oh, you refuse nets as well? We'll do that. Okay, you're doing the demo next time. Hey, check out 9.37 real quick. This one. You can imagine taking shapes like this one. It's kind of a weird looking shape, right? Well, it doesn't show up very well against this. What's that?
It's a quarter or so.
Yeah, so we could also cut it off here and make it parabolic or whatever. So what if you take some weird shape like this, right? If you're wondering about this weird shape, you could discuss, in this case, notice what I did on 9.37 there. On part A, I said, well, let's write a polynomial instead of a linear equation. So you might be thinking, well, not everything in life is a linear equation. What would you do if something's nonlinear? Well, that's one way you could describe it. Jules, do these problems remind you of something you've seen before? Yeah. We do these same exact problems when we do resistivity calculations and resistance. So I know it seems crazy, but I'm going to basically do these exact same problems in Physics 163 for a different purpose. So I'm trying to foreshadow another class here. If you have time before tomorrow's class, before tomorrow's lab, please look at 9.33, 9.33 and a third, and 9.33 and 2/3. That's the problems at the bottom of page 46. If you need a shot, an image of those, Jacob, I'll get you. You can just take a photo of mine. You know what I'm saying? I got one there. Are they in there? Yeah. Oh, okay. I can't remember which is in which. But yeah, and then watch those videos. And if you want, we're done with class. If you guys are really scared about coding and you want, I've got office hours now. I'll teach you some basics right now if you want. But yeah, do whatever. Get out of here. Watch the training vids at home. I hope that was kind of fun today. Oh, there it is. There's the one I was looking for. There it is.
You know what we want?
What's that?
Where's the spring?
The exams.
Oh,